We discussed earlier that MT schedule combines periods into blocks. Then the optimization uses these blocks as a reduced chronology. We have different ways to define how these blocks should be determined by setting the chronology setting to partial, fitted, or sampled. Note that as we choose one of these options on the MT schedule object, the user interface updates, and we have more settings to define that specific method. Let's dive into these to take a closer look. We'll start with the partial chronology. In the MT schedule, when we choose partial, we have the option to choose one duration curve each day, week, month, quarter, or year. We can also specify how many blocks should be in that duration curve. Let's consider an example using these settings of one duration curve each month and 12 blocks in each duration curve. We start with a time series of load or price data. In this case, we have hourly load data for an entire year. Because we have chosen to have one duration curve each month, we'll take the time series data for the first month, January. Using the hourly load data, we create a load duration curve. Note that by reordering the load data in this manner, we lose any notion of chronology within the curve. Then the LDC is fitted with the 12 blocks that we specified. The method used to slice the LDC into these blocks is controlled by the LDC slicing method. There are two LDC slicing methods that we'll go over next. The first LDC slicing method is peak-off-peak bias. The slicing is done with a bias on placing blocks at the top, peak, and bottom, off-peak, of the curve, with less blocks in the middle, so as to better preserve peaks and off-peaks. This method automatically pins the top peak value so the first block represents the peak load. The remaining blocks are distributed using a quadratic formula for spacing so that the block slicing is biased towards the top and bottom of the curve. The second LDC slicing method is a weighted least squares fit. This method is a more sophisticated approach to fitting the step approximation to the duration curve. The method performs an optimization that minimizes the sum of squared errors, for example, the square of the difference between the original curve and the step function approximation. Note that this is the same load duration curve as before, but with the weighted least squares fit slicing method. There are additional settings that can be defined. For example, if pin top is set to -1, once the number of blocks equals or exceeds 7, the peak will be pinned automatically. Let's review how the reduced chronology is created and used. Let's start with a 1-year step with hourly load data. That's 8,760 hours of load data. We chose to have a monthly load duration curve, so the time series data from the first month is used to create a LDC. Then the LDC is sliced into the number of blocks specified. In this case, that's 12. Note that each hour from our original data is mapped to one of these 12 blocks. Now if we consider the rest of the year, 11 more load duration curves are created, one for each month. And each LDC has 12 blocks, so we end up with 144 blocks to represent the year. So these 144 blocks are used as the reduced chronology in the MT schedule optimization. Let's consider an example result from the MT schedule. In this case, we see the generation across the 144 blocks. Remember, the block is the finest level of resolution in the MT schedule, but because earlier each hour was mapped to a block, we can then map block results back to the hourly. In this way, we can show MT schedule results as a chronological output. It's important to note this because the hourly results you see for the MT schedule are mapped from their corresponding block level results. The next chronology setting we will cover is the fitted chronology. With this setting, the input load or price series is fitted with a step function using the weighted least squares technique, so that the total number of simulation periods per day, week, month, quarter, or year is equal to the block count setting. Note that only contiguous intervals are aggregated into blocks, thereby preserving chronology. In this example, we have chosen to fit the step function each month and define 12 blocks across the month. We have the time series data in blue and the fitted chronological blocks in red. Note that for fitted chronology, we would recommend increasing the number of blocks to better represent the original time series. This trade-off of detail in the number of blocks and runtime should be tested. There are also additional pin settings for the fitted chronology. The user can choose how many of the top peak and bottom low load values must be kept and not be aggregated. So in the green blocks, we see more peaks are kept, but overall there is more smoothing across the other blocks. The user has different options of how to represent this time series. The blocks will then be used as the reduced chronology in the MT schedule optimization. The final chronology setting is sampled. Samples are taken of the days, weeks, months, years, as controlled by the sample type setting. The number of samples taken is set by the reduced sample count, which in this screenshot is 4, and or the reduction relative accuracy. Sampling is done statistically such that like periods, days, weeks, months, are removed, leaving a sample set that is representative of the variation in the original load or price series. Note that the loads in the formulation are the weighted average of the reduced and preserved samples. Let's consider a few examples. In this example, we are reducing 365 days to 6 typical days for the year. The blue time series is the original input data. Each day in the year is replaced by one of the 6 typical days that is most alike. This is shown with the orange line. The total number of periods to simulate in the MT schedule is 24 hours times 6 days, so it's 144 blocks. In this example, we consider 1 typical week per year. The algorithm reduces 52 weeks to 1 typical week. Again, in the graph, the blue is the original time series data. Each week is replaced by the 1 typical week. Then for this example, the total number of periods to simulate is 1 times 24 hours times 7 days, which is equal to 168 blocks. In this final example, we consider a typical month. So the algorithm reduces 12 months to 1 typical month. For this example, the total simulated periods are 1 times 24 hours times 31 days, which equals to 744 blocks.